All right, hello class. We are going to start chapter 3, and we have 3 interesting applications that we want to do here in chapter 3. First, we want to do local extrema. Second, global extrema. And third, optimization problems. So these are our first big set of applications for using our partial derivatives and our directional derivatives. So let's first start off by thinking about what a local extrema is, and we'll be able, as usual, extend some ideas that we know from R2 that'll help us here in R3. So I wanted to start off first with the visual aid and some reviewing some ideas. So, all right, so I made a 3D surface here. I just took a book and put some junk under it, in this case, apple and an orange, and used a cloth. So you can do this at home with a towel or t-shirt or something and just throw some stuff under there, shoes, something to make an interesting surface. And so maybe let's review a few ideas. So some of our key terms that we know at this point, we know a critical point. So a critical point is a place where both first partials, f sub x and f sub y, are equal to 0. And those first partials are slopes of tangent lines restricted to be in certain perpendicular planes. And so we have maybe one this way and one that way, but they both have a slope of 0, creating a horizontal plane. So critical points, where are critical points on this surface here? And so we can see right here at this, looks like a flat place. Over here at this one, another flat place. And then maybe in here, it's not quite as smooth maybe to see, but it looks like we do actually have a saddle point in here, which imagine yourself actually on a saddle. So there will be a min in one direction and a max in the other. And so I could put my legs right here over this, and then I would be holding, right here is the min part, this part is the max part coming over. So we have a saddle point. Let's see, some other key terms. So we're going to add in chapter 3, a few key terms are local extrema and global extrema. And so local min, local max. Extrema just means extreme in either direction, so max or min. Same things that we meant in R2 will mean here in R3 when we talk about extrema. So a local min, do we have any local min on this? I don't see any local min. Those would be places for valleys. And you'd have a horizontal tangent plane, but you're also smaller than all your neighbors. So on the other hand, we do have a local max right here. So this, to be a local max, you have to be at a point and you would look around and all the way around 360 degrees, spinning around your compass points and say, I am taller than all of my neighbors. And that's the case here, which makes this a local max. This is not a global max though, because if you're on this mountain peak and you look over in this direction, you'd see that this guy is the taller one. It turns out this is a global max here. So if you are bigger than everybody on the whole domain in which you're described, which we'll often call that a region R in this chapter. And so there may be a restricted region over which we're interested in the surface, rather than from minus infinity to infinity. So if these were to level out, let's say the surface levels out in all directions. So we have a couple peaks here, and then it just levels out. If that were the case from minus infinity to infinity for x and y, then we'd have a global extrema over the entire domain. But sometimes we'll restrict ourselves. And so we might create a region. So give me a second here. I'm going to use this shoestring here and create a region over which we're interested. So maybe on this surface, we're interested in this elliptical sort of region, which would actually be defined in the XY plane, and the surface would live over that region. If that were the case, then if the region R is defined by the shoestring as sort of this elliptical shape here, then it turns out that this actually is a global max over that restricted region. So this can be our goal in this chapter, is to find local max and local min, global max, global min, and then to solve what are called optimization problems, which are very similar to what you learned in Calc 1. We're just going to extend from R2 to R3. Okay, one other idea I just want to review while I do have the shoestring is to talk about paths on this surface. So if I were just to make sort of a meandering path, this is now not a restricted region, but the shoestring is representing, like, say, a hiking trail on this surface that you're moving about. In this case, we can review a couple other concepts that we learned in chapter 2. When we used partial derivatives, we talked about gradients. And so a gradient tells you the direction of steepest ascent if you're going in the positive gradient. If you use the negative gradient, it's steepest descent. So it would be at any particular point on the surface, you'd pull out this compass, which is actually a special gradient compass. Rather than pointing north, it points you to the direction of steepest ascent. If you just go in the complete 180-degree opposite of that, it would be steepest descent. So at any point on this surface, I'm hiking along this trail, starting on the back of the ridge here, come around the front, and maybe I decide to stop and rest. I pull out my gradient compass right here, pull it out of my pocket, boom, and it points me in the direction of steepest descent. So even though the trail goes this way, if I wanted to ascend to the peak to take a picture or get an aerial view, it would be going this direction. And the descent would be 180 from that. Then I hike a little further along the trail, ask myself pull out my special gradient compass. The direction of steepest ascent from this point would be coming up this little ridge to the global man, so it would point me this way. So the trail sometimes goes with the gradient, sometimes goes away from it. If you're going with the gradient, most of the time you'd be hiking a very steep, difficult trail. And so another thing to do just to practice at home, you could, to make sure you know your vocabulary and get visuals for these, is do the very same thing. Take out a towel, a t-shirt, put it over some junk, grab a shoestring or string. I tried a charging cable because I figured everybody's got one of those, but they're really stiff. They don't lay as well. So one thing you could do, last piece, is you could define the path of steepest descent. So let's imagine we're hiking on the surface. We get to a particular point, say right here, which is pretty close to the global max, and someone gets injured and we need to do emergency evacuation. What is the steepest way down to descend this surface, down to maybe the parking lots in the flat area over here? We want to get down there. Just making sure that you can do that, you should be able to visually see the steepest descent path would be always move in the direction of the negative gradient, and it's very easy once you see the visual surface to know what direction to move. Okay, so lots of review of concepts here, and then with the next video, we'll start getting into calculating. Our first one is to figure out this one over here. How are we going to get these local extrema? Right.